Good afternoon on Friday, the 17th of April. It's still, well, it was snowing a little while ago. I'm trying to squeeze this in just before I take off on my trip, finish some packing and so on and so forth. So without further ado, this will get posted and it will be lecture 12, I guess it will be numbered as, if I'm thinking correctly. At any rate, what I want to do is just get right into the material, and I will also include some overview of upcoming homeworks, Project 2, and hopefully get all the way down into the start of Appendix A. We'll just see where this takes us. So getting over to the notes, the next set of topics is frequency synthesizers, and this is a logical extension from phase lock loops. And what frequency synthesizers allow you to do is generate a stable yet programmable frequency source. And this is the way most radios tune today. They don't tune with an analog capacitor, changing the frequency of an oscillator. They generally will tune with frequency synthesis and some sort of frequency synthesizer, such as this technique here. It's called indirect synthesis. With indirect synthesis, we use the phase lock loop to create a stable frequency source, as I pointed out in the bullets above. And the basic block diagram is this. This is more of an abstraction than what we've seen in the phase lock loop so far. We have the phase detector, loop filter, and VCO across the top. And the input to into the phase lock loop is called the frequency reference. It's not a signal coming in, a received signal. Instead, it's a reference, like coming from a crystal oscillator in the electronics. And I'm just denoting the frequency division by M. So we take the reference and divide it by M. It might be a 10 megahertz reference. We divide down to 1 megahertz or whatever the requirements are. So the input to the phase detector is FREF over M. And now what the phase lock loop is going to be doing is it's going to be trying to lock to a frequency that matches FREF over M. So we come around the loop, we go into a loop filter, a VCO. The VCO is going to output a frequency called F out, and it's fed into a frequency divider also, and this is generally a programmable divider, one that you can use a microcontroller to set the register value of division on. And we're dividing by N in the model, so F out over N is the frequency coming out. That goes to the phase detector. The two frequencies have to match for the loop to lock, so that says we're saying FREF over M equals F out over N, and so the lock equation is shown right here. It's just saying that when we're locked, F out is going to be N over M times FREF. So you can kind of get an idea of some of the things we can do with this. M is going to set our frequency step size, and then N is, like I said, the programmable divider. So FREF over M will be the step size. If N increments by one integer, we'll shift the frequency by FREF over M. So let's take a hands-on example immediately, because the math here is not really all that complicated. Suppose we want to provide a local oscillator in a FM broadcast band receiver. So we want to be able to tune from 88.1 to 107.9 megahertz. We want to use an IF at 10.7 megahertz, and we want the channel spacing to be no less than 200 kilohertz. We prefer 200 kilohertz because that's the channel spacing in broadcast FM. So we'll choose high side tuning. So we're going to add 10.7 to the range that we desire. 88.1 plus 10.7 becomes 98.8. Marker back on again, and then on the high end of the broadcast band, 107.9 becomes 118.6. So and then we're going to constrain this, so the step size is 200 kilohertz. 100 kilohertz or 50 kilohertz would also work, but this would make the divider have to do more work. So now what we're going to do is redraw the block diagram and put specifics in it. We're going to make FREF over M be exactly 200 kilohertz. Like I said, that is our step size in the synthesizer. We're going to have the VCO come out and produce F output, which is going to be our local oscillator frequency. And we could get by with a very large divide ratio here, but a more typical scenario is to put in this mixer. So this mixer here is going to produce an offset frequency from F out, and I'm calling that offset frequency F mix. So in this case, I'm going to choose F mix to be F out minus F offset. So this is the difference frequency of F out and F offset, and we're going to lock to F mix after we divide its frequency by N. So when we put the two equations together again like we had before, to replace F out, solve for F out in this equation up here, F out is going to be the N times FREF over M plus F offset. Just doing the algebra on this and making the substitution. So this tells us our output frequency will be N over FREF, N times FREF over M plus F offset. So the offset is just making it more convenient for the divider to work with a lower frequency range. In days long ago, when we didn't have digital dividers that would maybe divide at really high frequencies, the offset also provides a means to lower the frequency into the digital divider in the synthesizer. So at any rate, solving for F mix, it's going to be N times FREF over M, and then this is the F out as said before. So we've got FREF over M being 200 kilohertz. That's in the denominator now as 0.2 megahertz. And then we want to solve for the maximum and minimum integer divide values for our divider, and this equation does that for us because we're going to put in, from up here, we're going to put in 118.6 for the upper range and 98.8 for the lower range of the LO. Subtract 98, divide by 0.2, so that's a divide integer of 103 to produce the highest frequency, and then when we use the low end, we will get a divide ratio of 4. And that's all there is to it. So the programmable LO will just be set with a keypad or a digital tuning knob, stepper knob, and it runs from 4 to 103. Make sense? Just a nice solution, a common solution in today's radio environment. There's some other tricks you can pull with a phase lock loop that are not particularly exotic or anything. It's just building on the same idea that a basic first order loop, if you feed it an input frequency, a clean signal that's not a received noisy signal, we can make the VCO lock to that signal very easily with the loop amplifier and a proper phase detector. So here's one application where we're going to do frequency multiplication by 3. So we take maybe a sinusoid, convert it to a square wave. The square wave is going to produce odd harmonics, so it's going to produce a third harmonic. And the idea here is that we're going to be having our VCO close to 3 times FC so that it will lock onto this harmonic rather than the fundamental over here. So the loop locks up to the third harmonic, and then the output of the VCO is controlled by the input square wave or sinusoid as 3 times that frequency. So it's a frequency tripler in terms of the sinusoidal frequency. We can turn this around and do division if we want to too. So we can put in an input. In this case, I'm showing it as a pulse train, which we know has many harmonics in it, all spaced at 1 over the period T naught, but we get, with the pulse train, remember, we get the first null at 1 over the width of the pulse train. In this case, the idea, though, is that we want the VCO to be centered on half the carrier frequency that we have coming in, and we'll be locking to this low harmonic at FC over 2. So same idea, we're just putting the VCO in the area of a subharmonic, in this case FC over 2. A more general application that I think the book goes into is called frequency compressive feedback. This is an old application of phase lock loops for FM and PM demodulation indirectly using a discriminator inside the loop. I'm electing to not go through that. I didn't give you any homework, but this is just written out in the notes. I think it's still in the book. It's possible that was removed from this latest edition. Next topic, though, for phase lock loops is carrier recovery for double sideband, and then we'll move this into digital demodulation, which is related to Project 2. So suppose we have just a double sideband signal that's not necessarily digital, it's just got a message directly times the carrier. We know that with double sideband, and of course this is part of the exam 2 topics, we can't recover the message from this without getting a coherent carrier in our hands. So we need to get a coherent carrier. So we can use a phase lock loop to derive a coherent carrier from this XR of T signal. So there's 2 popular types of means of doing that. One is called a squaring loop, the other is a Costas loop. Costas is the name of the guy that invented it. The squaring loop looks like this, the upper block diagram. You take a copy of the input signal. The upper path here is the signal we want to demodulate coherently. In other words, you want to make that cosine omega CT have theta equals 0 if we're tracking, or actually theta and phi, the input phase, should be equal to each other. So phi is going to try to estimate, or theta is going to try to estimate phi. At any rate, we squared the signal, and now we have a double argument in the cosine, so we have 2 phi. The amplitude of the sinusoid gets squared, so now we have the message squared. And this is kind of the key to the operation of this whole squaring loop. We're going to have a double frequency, and we're going to set our loop to lock to the double frequency. So we're going to have a frequency doubler in here on the output of the VCO, driven by, this is called a quadrature hybrid in RF circuits. A 90-degree port is going to drive the doubler, and it will be a sine coming out of this port because it's at 90 degrees, and then the 0-degree port has the cosine coming out of it, and that's what we need for demodulating coherently. At any rate, the loop locks up to 2 omega c in the end, and then it will be coherent, and we can do our demodulation. The more popular of these 2 is the Costas loop. It's actually in a project I'm working on right now. It's just like bread and butter in digital demod, especially for BPSK type waveforms. At any rate, this wraps the operation of the squaring loop inside an in-phase and quadrature mixer pair. So we have cosine and sine, again the same quadrature hybrid. We have the VCO driving that, and this will lock up to a phase error, which is 2 times psi, in this case, in the way the model is set up here. So there's no doubler required on the VCO. This will produce the signal right at the carrier and demodulate with sine and cosine the received double sideband signal. Then this mixer out here produces this error signal. Again, m squared of t shows up just like it did over in here. So it has the same foundations. Now the foundations are what are important to make this work. M squared of t must contain a DC component, because then that says that a DC spectral line will be formed out here in the squaring of the signal, and that spectral line can then go through this multiplier acting as a phase detector and lock to the sinusoid at 2 omega c. The details are something you can play with in your spare time in Python to see how this stuff works. The costless loop accomplishes the same thing, but we have to have these two low-pass filters to throw away the double frequency terms from the mixers here. It's a little bit more complicated. The guy Costas invented this, so it was something that somebody with your understanding and background could go through the math on this. This times this will produce out of a difference term, which is the sine 2 psi, and then there's a term thrown away at the double frequency term or phase term, which the loop filter suppresses. I'm thinking back to the trig identities. That'll be suppressed. At any rate, the loop can lock and track small frequency errors between the input and the VCO quiescent frequency. Again, the DC component is necessary. In digital modulation, very similar to double sideband, if we have a simple scheme known as binary phase shift keying, which is talked about in Project 2, it is like double sideband, because here the message is just a pulse train, a train of pulse shapes times d of n, and d of n is just plus and minus 1 amplitude random data bits or data bits. And in this case, I'm just showing it as a rectangular pulse shape. So it might look like this. The message just looks like random bit stream of plus and minus 1 amplitudes, as opposed to an analog message. We played with this in chapter 3, if you recall, when we were first looking at double sideband, and showed that it works well with a coherent demodulator, and without it, a non-coherent demod, you can't recover the data bits. So it's very vital to have the coherent demod for BPSK. And if you take this up into the discrete time domain, what you end up doing for this exact same type of waveform is you end up having a front end which has the in-phase and quadrature set up for mixing the signal down the baseband, the low pass for the in-phase and quadrature waveforms. That's what Ri is the in-phase from the cosine multiply, and Rq is the sine from the sine multiply. Then we take it to the discrete time domain with A to D converters running at some sampling rate, f of s, and of course f of s and the low-pass filters need to be consistent for Nyquist sampling. So we end up with a complex waveform. This is our complex envelope. This kind of parallels what Project 1 was doing with the single A to D of getting just the real signal and then forming the complex or imaginary part with the Hilbert transform, the analytic signal idea. So this and part 1 or problem 1 of Project 1 is the parallel to this, getting the complex signal. Once you have the complex signal, which you have now played with in Project 1 if you've been working on it, or some of you have turned it in, now we can proceed to have carrier tracking for coherent demodulation, and it could be for BPSK or higher order digital modulation. So in this case, this is an example of an nth power digital phase lock loop for carrier phase tracking. The lower block diagram is a feed-forward structure. I'm going to explain briefly how they work. This is like the squaring loop. So we take our signal and we take it to the nth power. We take the imaginary part of that, and that is going to give us an error signal, an error waveform for driving a digital loop filter. This is just a lead lag loop filter in the discrete time domain, equivalent to the one we were looking at the end of class this past Tuesday. And then a numerically controlled oscillator, NCO, is formed with this accumulator structure to integrate from a control voltage effectively into phase. And then the lookup table is just to say we'll take the accumulator output, which generally is like 32 bits or 48 bits in an FPGA maybe, and go to a sine cosine lookup table and produce sine and cosine values that will form this complex sinusoid you see right here that will drive its phase and frequency to produce, to effectively remove the coherent, or remove the carrier coherently. So we have zero phase error left, we just have the data. This is a variation on that, and rather than using a feedback loop, this is a feed-forward carrier phase tracking. And what it does, it puts in the signal path on top an LTAP delay just to keep match to the delay that the bottom processing is going to throw in. And then we form the nth power operation by going rectangular to polar. We have a function to manage just the magnitude, and then we have a multiply by m to form the nth power operation. So in the phase domain, we're just going to multiply the exponent by m, and that's what this lower branch is. Then we reform it to an e to the j and bring the amplitude back in, or the magnitude back in, and bring the angle in, and then smooth it with a moving average filter, and then scale it by m to take the phase rotation on that, which was multiplied by m, and divided by m to take it back to remove that power, the impact of the power, and then we take the angle, or arg, of the cosine, and that then becomes our angle that drives the complex signal that is our complex sinusoid for demodulation. This should be a flipped sign effectively, and I don't have that shown in here. There should be a minus sign up here, so it's de-rotating the signal is the way it's best to think of it. It's rotating, say, counterclockwise in the received signal, and then you rotate it, counter-rotate it to try to get it to stop rotating at the output, and then you get your data back, or your waveform of interest. So a couple ideas there. Some of these things have been implemented in the synchronization module of the Scikit DSP-Com. Others are maybe in the notebook or something, in notebooks that I have. I don't think I've given you any of them, but they're out there. I'm thinking they're out there from the phase lock loops class, so I guess they're not available because none of that's posted right now on the website. Okay, before we go any further, I'm going to jump over and look at a simulation. And the reason why I'm going to look at that simulation is because it's part of the next homework assignment. So if we go look at set number 9, there's a question on frequency synthesis in here, very simple, but my emphasis right now is to just talk a little bit about problem number 2. Problem number 2 is working with a complex baseband phase lock loop, which is written in Python code already, and it's all set up for you in the Chapter 4 Jupyter Notebook. I added the figure that got omitted from the zip file just before I started the recording here, so we're going to go take a look at that right now. So what you're going to do in this problem is just simply extending what's already in the notebook. So let's go take a look at it. It's right over here. So we're going to look in Chapter 4. There's a section in there after the second order phase lock loop we were looking at on Tuesday. This picture is omitted, and it's now in the zip package. It's just this picture, so you're seeing it right here. It's a block diagram of the complex baseband phase lock loop. So takes in a complex sinusoid waveform. It could be digital modulation, analog modulation. It's just in complex form, kind of like in problem 1 or project 1. And then the VCO in this case is taking the phase and putting it up into a complex sinusoid return. It's the conjugate of it to get it to spin counter-rotate relative to this rotation, so it's trying to stop it. The phase detector, very similar to what we were just looking at, is formed from the imaginary part of what comes out of this complex sinusoid mixing action. Then there's a loop gain K, and then there's a loop filter, and then there's a 1 over S to represent which is actually an accumulator in the DSP domain that represents the action of the NCO or VCO. So these are just writing out the equations and the math, and this is just taking you through what I wanted to demo out of this complex baseband phase lock loop. What I want to have you look at is what I'm going to describe right now, and that is that we're going to put an input in where the message is an angle modulated message. It's going to be an FM modulation, and it's going to go up right inside in place of theta of t here. So it's going to be angle modulated, and what we're kind of striving for is seeing that under linear operation, and I can't draw on this because it's a Jupyter notebook, under linear operation of the loop, the VCO control signal, E of V, will be the sinusoidal response of the closed loop system of the phase lock loop. So if I put in an angle modulation and give it a frequency FM, some amplitude AM, and phi can just be set equal to 0, what we're going to see for the error voltage coming out is just going to be the amplitude of the input modulation wrapped up inside the complex exponential with Kf and Kv in here just to normalize it, because the Kv is from the phase lock loop's VCO, and Kf is the modulator constant in the phase detector. It ends up being, if I rewrite that, it's going to be Fd, the deviation constant, coming in the modulator, and Kv prime. But the really important thing is that we're getting as the magnitude of the output voltage from the VCO or from the loop filter is going to follow the magnitude of the closed loop system function of the phase lock loop. So as FM changes, the output amplitude will change. And I explain that in more detail here, but I'm just going to take an example. Here I'm just going to take a look at what we expect to be getting for the first order phase lock loop. We expect it to be just a low pass filter. And I have it written down right. Well, let's see. Maybe now that I'm looking at this was something else I added to the code, because I've got it. Now it is correct. It's normalized by Fn, so it is a low pass filter. F is what's varying in here, and Fn is just a gain coefficient, but it's a first order low pass filter. Is what I intended to do. So this is what we know for the second order loop. It will be a second order response. And this is what we can measure with this complex baseband phase lock loop. We can see that it will pass through the input modulation, FM modulation, but it will get shaped by the closed loop system function of the phase lock loop. So here I set up a simulation. I'm not going to put in any frequency steps or anything. I'm just going to start off by putting in pure modulation. So this is the message I'm putting in. This is FM modulation. I'm I'm putting it on a carrier frequency F0, and then I'm going to add to it some modulation. And that modulation is embedded inside of phi here. And this is just the constants associated with the FM modulator. So this X is coming in over here as the input, complex sinusoid. I'm setting AM equal to 1, FT equal to 1, perfect for our application. I'm going to set the frequency of the modulation equal to 1, and then I'm going to apply it to the complex baseband phase lock loop, which is part of the synchronization module. So the signal comes in as X. I set Fs, defined here to be 10,000 hertz. I'm setting, let's just refresh our memory. What are the attributes? We have the third attribute is the type of loop. I'm going to set it as a first order loop. And then I'm going to set the phase detector gain, or VCO gain, equal to 1. And then I'm going to set the cutoff frequency of the loop equal to 10. So it's going to be a loop KT of this first order loop is 10 hertz. And the damping factor doesn't matter at this point. I think in the homework problem I may have you do something slightly different. In the homework problem, you start with the first order loop, then you switch to the second order loop, and you're trying to measure it in the simulation and see that it follows the expected response of the first and second order loops respectively. And that's what I've already placed in the notebook over here. That's why the math is in here. This is the response you expect, the magnitude of this from the second order loop, and the magnitude response to the first order loop is further up the page here. I'm not quite laying my eyes on it like I was hoping. It's sitting right here though. So what we'll do in the loop, I'm going to put in 1 hertz for the modulation, run the simulation. This is the VCO control voltage. It's following the input FM signal, and if I go ahead and look at the magnitude of this VCO control voltage, I see that it's, with the normalization constants, it's essentially 1. And so the magnitude in dB is like minus 0.04. The peak value we expect to be about 1 when FM is much less than the natural frequency of the loop in hertz, Fn, and we're seeing that. So what I want you to do in this problem though is you're going to sweep over a range of frequencies, and it's okay to just take data points manually. So here I'm at 1. If I set it equal to 10, I'm at 10 hertz, and what do I expect for a first order low pass filter that has cutoff at 10 hertz? If I'm looking at the response of that filter and I plot it, or I just evaluate it right here, it's like 0.707 or very close to it. Or if I just put it in dB, it's about minus 3 dB. So you're going to just get more points. So you're going to build off of this. You might put a loop around all of this and then automate the process if you want to get more points and do a plot. I think I probably did something like that in my solution. Okay, we'll come back and look at this in a bit. We're going to jump over back to the notes, and we're going to talk about interference and then preemphasis and de-emphasis in angle modulation. So interference in angle modulation is sort of the parallel discussion to what we had at the end of chapter 3, where we were assuming that besides our desired carrier term with modulation embedded inside of it, we would have an interference or jamming tone. Here I'm assuming there's no modulation just because I don't need to look at that. I just want to see what the impact will be when I have the interference and I have a discriminator or some type of angle modulation, demodulation. So I expand this out in terms of an envelope like we did in the end of chapter 3. We have the envelope the complex envelope is right here. We have just the pure carrier with the interference, and then we have, on the imaginary part, we have the sign of the interference frequency and its amplitude. So that's the real and imaginary parts. We form the magnitude of that. That's our envelope, something you explored a little bit in Project 1, Problem 1. And we can get our handle on the phase. In this case, we're interested in the phase, not the amplitude, because we're doing angle modulation. So here our main focus is what is happening when we have phase present. And here I'm just doing a power series expansion on arctangent, just to kind of refresh our memories a little bit on how that would work out. The bottom line is that if this is a small quantity, which is what we're going to have in our first scenario is down here. We have the carrier much larger than the interference. In other words, a strong signal, weak interference. What's going to happen in this expansion of the arctangent, we're going to essentially get back out, just an angle which is like X in the power series expansion. And what that says, the bottom line, it says we're going to get the constant amplitude from the unmodulated carrier that we care about, plus the interference will come out of the math, and the phase is sitting over here as the cosine of omega ct plus the angle. The discriminator is going to go after the interference term. So in this case, what's going to happen is we will get our hands on the derivative of phi, and then we'd follow that with an integrator to go back to the phase domain. In the case of the FM, we get just the signal directly. And I kind of got a little bit, I confused myself a little bit, because what we're doing here when we look at this, we're interested in this term here, and it's the reason why we're interested in it like that is because we're doing this expansion and we're not modulating the carrier. So for small values of interference, what happens is the interference comes through in the PM case and in the or the PM case up here and in the FM case down here. But AC is much larger than AI, so this term can be made negligible. There is one interesting side note, though, that I want to make, is that in the case of the FM, we see this proportionality with the frequency of the interference, and this is the frequency of the interference relative to our signal of interest. So as the jammer gets further away from our signal, the impact of it actually gets larger. And that's what I'm saying in this bullet here. Amplitude of the tone is proportional to the offset frequency. And if Fi is greater than W, the bandwidth of the message that we are wanting to demodulate, the low-pass filter removes it. Now, this is for the strong signal, weak interferer case. When the interference is similar to and larger, then the above analysis doesn't hold. The power series expansion can't serve as a point of approximation. Instead, we have a full complex envelope that now would say have this unmodulated carrier plus our interference. And if we go look at the phase or the angle associated with this complex envelope, it becomes what we saw earlier, except it's going to be fully the arctangent, fully the arctangent of this ratio. And there aren't any really good simplifications. It's just kind of turns into a bit of a mess. When AI is approximately equal to AC, I've just had the computer draw some pictures. This is what the interference is coming through. this is for a small value of interference relative to the carrier, so 0.1 of the carrier amplitude. This is phi of t, this is the derivative. This would, be PM, this would be FM, because we differentiate it to get the frequency deviation back. We increase the amplitude to 0.9. It's starting to distort phi, and of course when we take a derivative with these rather rapid shifts, we get these spikes. When we take the amplitude greater than the amplitude of the carrier, it gets even more extreme. So what we see is these things are referred to as clicks. The discriminator output, when we're trying to recover it with a strong interferer or near equal amplitude interferer, introduces clicks, and in general the signal gets lost. We're said to be operating below threshold. We may notice this when you're listening to an FM station and you have interference nearby and you can't receive anything. You'll hear a clicking sound, or you'll just hear some buzzing or something in the background. So to take this a little bit further, suppose we put in modulation now plus the interference and then look at the angle. So here I did the same pictures, and now I'm wanting to see what's happening as the interference amplitude changes relative to an angle modulated carrier. So we see the angle modulation, cosine omega m here, and then the derivative, I'm just looking at it for FM right now. Forget, this is only for FM, so I just have the derivatives. I bring the amplitude up. It starts off looking good. As the amplitude gets up even to 0.1, it's starting to get a little distortion coming through, and this would be audible if it was analog modulation. As it gets up to 0.5, it's even more obnoxious. Then when it goes up to 0.9, it's pretty much wiping out the signal of interest. You get very little of your original sinusoid through. You get a lot of other things coming through from the interferer, which is at 3 times the frequency of the modulation. And I don't feel like I did a great job of talking about it, but if you have to deal with this, you may end up doing simulation just to understand what's going on. Obviously, you don't want to have the interference get very strong, otherwise you've got problems on your hands. So the next topic we'll move on to is the use of pre-emphasis, and part of the motivation for this comes from the jamming we were just looking at. We've seen that when AI is small compared to AC, the interference level of the interfering signal in the FM case is proportional to Fi. In other words, it gets bigger as the frequency gets higher. So we can generalize the single tone interferer to background noise. Suppose we're talking about a weak signal and the noise is very noticeable at this point. So the noise that gets processed through our FM discriminator will actually grow in amplitude as we go up to higher frequencies. And I think most of you can relate to this, because when you listen to an FM station that's very weak, or you're just tuning, you will hear a lot of noise, and you tend to, the noise seems omnipresent, but it's not low and rumbly, it's higher in frequency. So when you're listening to broadcast FM, they've long ago came up with a way of compensating for this proportionality in the interference or in the noise. The wideband noise has the higher frequencies. It gets more emphasis in the demodulation process. So what do they do in the FM broadcasting? They pre-emphasize or boost the high frequencies before they send it out over the transmitter, with the intent being that they're going to equalize the higher frequencies. In other words, knock them down in frequency so the noise is not so noticeable. The idea with the pre-emphasis is to mask over the noise by emphasizing the higher frequencies so that they'll be covering over the noise better. The block diagram here kind of shows you the picture of what's going on. At the modulator, we pre-emphasize with this analog circuit. So we take the higher frequencies above F2 and we're boosting them up. We have a transition band we go through, and then at the receiver we start rolling off right at F1, and that gain flattens it so that up to F1 it's flat, and then we're just rolling that off because that's above where we want to have audio content. So this is the pre-emphasis, de-emphasis. So you have the pre-emphasis on the one side, and then you have the de-emphasis, just a low-pass filter on the receive side. And the idea is we're trying to improve the interference to noise ratio. I mean, the output quality with interference or noise by having the pre-emphasis to overemphasize the high frequencies so we can knock them down. And we're using a masking technique of masking over the noise by pre-emphasizing. This was used, it's used today in commercial broadcast of FM. It was used, and this is going to date me for sure, but tapes. You used to listen to cassette tapes in your car, and magnetic media has the same phenomena. When you recover it, you need to use pre-emphasis and de-emphasis. So same ideas have been used elsewhere in communication signal processing. So the next topic, and this kind of is heading down the home stretch to the end of this chapter, is multiplexing. So multiplexing is very common. It's kind of like the continuation of the discussion of time division multiplexing at the end of chapter 3 for digital streams. When we have analog streams or analog waveforms, we use what's called frequency division multiplexing. So let's take a look at that. FDM has been around a long time, and it's used everywhere. It's used in cellular telephony. It's used in satellite communications, and it's used in commercial broadcasting. So the idea with FDM is we're going to locate a group of messages on different subcarriers and then sum them together to form a baseband signal, and then modulate that onto one single carrier. So this is the block diagram. As I start going into this, I'm inclined to say let's go over and look at the homework problem you're going to have to do on this. It occurs in set number 10. In set number 10, you have a problem where you're going to combine a baseband, a 40 kilohertz carrier base signal, and a 70 kilohertz subcarrier base signal all into an FM modulator. And you're going to draw a block diagram of how you would demodulate that. And I'll continue that thought after I get through talking about the basic ideas of FDM. So here, all three modulators, 1, 2, and 3, are going to be on some frequency, but one of them could actually be at baseband. And it's common that one of these would be at baseband. And then you just simply sum them together. They're all on different frequencies, and they don't collide with one another, so they can be superimposed. And then the whole superposition of all of them, a little bit like the homework problem here, all three signals are disjoint from each other. They're not overlapping. So those can get combined together and go out through an RF modulator. We can think of it as the bandwidth will be the sum of the bandwidths of the signals, and then this will get applied to some sort of modulation. If it was FM, it would be Carson's rule. If it was double sideband, the bandwidth would be just 2 times B, and so on and so forth. The receiver demodulates the composite signal, and then we separate it into subcarriers using bandpass filters, and we end up with this block diagram. So we have some sort of demodulation for whatever the RF modulation was, and then we will separate out the individual signals so they don't interfere with the subcarrier demodulators. And the term is subcarrier because that's a carrier within a carrier. So the subcarriers are carried by the outer carrier. So we demodulate the individual signals off of their respective subcarriers. If all of the subcarrier modulations were using single sideband with no guard bands, we would get an extremely efficient modulation scheme because we would pack all the subcarriers together with maximum efficiency, and then we could send them out on an RF carrier. And this is exactly what the telephone company was doing for decades. The PSTN, as it's known as, Public Switch Telephone Network. This is the way they were sending signals across the country and in neighborhoods too, but they were microwave carriers were used to send multiplexed channels from point to point across the country. Now we use fiber optic, but wavelength division multiplexing is available, and you can put subcarriers on a fiber optic as well, so you can carry subcarrier signals in a fiber optic cable, or you can just have a big giant digital multiplexer. You have different options here. So as I'm saying here, you can have combinations of analog and digital. So with analog, you'll have AM, double sideband. That's a typo that I haven't seen before, but double sideband. And angle modulation, FM and PM. So there's lots of variations in this. So let's take a look at a commercial application that's been around since about 1948, I think, is when FM stereo broadcasting came into being for the commercial FM broadcast band. So the way FM stereo works is you take the left and right channels and you send them through this matrixing, which is just basically saying we're going to send left plus right, which is referred to as the monaural signal, and then we're going to send left minus right on another channel, and we're going to do this using frequency division multiplexing. So left plus right goes straight on through and comes out to the FM modulator. Left minus right gets put on a subcarrier that's at 38 kilohertz. And then we also send some of the original subcarrier frequency at 19 kilohertz along for a ride. Why do I say along for the ride? We don't really need this, but if we don't send this, then we have to coherently demodulate the double sideband that we're doing here. I don't know if you got this in your mind, but this operation right here is just our double sideband modulator, right? We're going to send a signal L of t minus R of t, modulating it on a 38 kilohertz carrier. So that's double sideband. To get the signal back in perfect shape, we need to coherently demodulate it. So what they do in FM is they send the 19 kilohertz pilot as a reference that can be filtered in the composite signal to either lock a phase lock loop to it or simply make a nice narrow bandpass filter that can then form a sinusoid that can be frequency doubled and demodulate the information that's on the 38 kilohertz over here. So that's what this block diagram here is showing you. Before we move on from that, just notice that, remember, FM stations, this will go on to the FM modulator, but we want to make sure that the bandwidth occupied here from 0 up to, say, 53, along with the deviation constant and Carson's rule, gives us something that fits within the 200 kilohertz wide allocation. So the single-sided bandwidth should be less than 100 kilohertz, so it can sit on 200 kilohertz spacings when you consider it at RF. So this looks like it fits no problem, but remember this is going to go into an FM modulator and the bandwidth will expand. So here's what the receiver does. FM discriminator gets back all three of these signals, separates them. The left plus right gets separated with a low pass. A bandpass filter gets access to the 19 kilohertz pilot, and then a frequency doubler produces 38 kilohertz subcarrier that can be used to coherently demodulate the left minus right. And that comes out of a recovery low-pass filter over here, which is part of the standard coherent demodulator for double sideband. And then the inverse matrixing operation gives you access to left and right. And then if you just want to send out the monaural, you get that. Or if your receiver doesn't support stereo, it just gets the left plus right. I don't know if you've been thinking this through, but radio standards generally have to support legacy. So the legacy FM broadcasting was sending a monaural or left plus right signal. And then when this was invented and added to the standard, people that had the FM stereo receivers could get access to the stereo sound. And I can remember way back when I was very young, my grandfather, who lived in Chicago, liked to listen to symphonic music, and there were lots of FM broadcast stations that did stereo. Not that I grew up in 1948, but as it became more and more popular, essentially everybody broadcasts in stereo today, but he would describe it to me as multiplexing. That's how he described it. And so he was an electrical engineer, but he was an electronics hobbyist just the same. So this was considered pretty cool signal processing for FM stereo using all analog electronics. Nowadays, we have chipsets that do all of this stuff, and they have the synthesizer we talked about earlier for selecting the station, and it goes on and on and on. I'm going to show you both a hardware demo here shortly and maybe talk a little bit more about it. Here's another form of multiplexing called quadrature multiplexing, and this is the basis for most digital modulation schemes used across the spectrum, from cable to satellite to Wi-Fi and cellular. All of them use this concept. So this is probably even more fundamental than the frequency division multiplexing. It just says if we put a message signal M1 onto a carrier that's a cosine, and then we put another message signal N2 onto a carrier that's a sine, the sine and the cosine carriers are in quadrature. In other words, they're rotated 90 degrees from one another. And if we send that over the radio channel by summing those two together, all we have to do is coherently demodulate with the cosine to get back the message 1, and coherently demodulate with the sine in the low-pass filter to get back message 2. It looks extremely simple, and you're probably saying, does this really work? Yes, it does really work, because sine and cosine are orthogonal to each other. So to show that this works, all we have to do, and this is, it's worked out for you, but this is an example of how you figure things out and see if things really work. Just represent this right here with the sine and the cosine, and then come down here and multiply times, do the multiplication to get back the original signals again. So here I'm going to take M1 cosine minus M2 sine, and then I'm going to get the double frequency term, because I'm assuming I'm going to multiply by cosine. And then I can do the same thing for the second signal, but here I just multiplied, just looking at how I did this. I'm not remembering for sure how I did this. I multiplied by 2 cosine, and then I get these 4 terms coming out. So the cosine is sitting right up here, but it's multiplying times the composite received signal, which has got both terms present in it. So I've done all the multiplying things out, and you can see you get double frequencies on both the M1 and M2, but those will get removed by the low-pass filter. And then down at baseband, you get a cosine theta, and this, if you've got it coherent, this is going to be essentially 1, and that's going to be 0. So you've suppressed the quadrature signal, and if theta is just small but not identically 0, then this term right here is what's called crosstalk. That's just due to your angle not being exactly 90 degrees. And if you did the analysis for the quadrature side, in other words, multiplying by the 2 sign, it'd be the same thing, except it would recover the opposite, and it would do the same idea. It's interesting to compare double sideband or single sideband with quadrature modulation. With quadrature modulation, you're getting the same bandwidth efficiency that you get with upper single sideband and lower single sideband. But it does require a fully coherent demodulator to get the best performance. Otherwise you have crosstalk, and if you don't have it, if you don't have that, you've got garbage. You basically have 2 signals you're hearing mixed against each other, because just look what would happen here if this theta is rotating slowly and theta is rotating on the cosine. You're going to hear both signals mixed together. So you have to have perfect quadrature, and you have to do it coherently. Okay, let's take a look at some hardware, and I'm going to switch to my software-defined radio that I have plugged in. I think I had this up and demoed on the first day of class. I've got it plugged in. It's RTL SDR, and the app I'm running here is SDR++. And I don't know if it's getting picked up or not. I'm just listening to KCME. I'm going to stop it. But KCME is sitting right here. This is FM stereo right inside of this blob. I can't see the subcarriers because I'm looking at it after it's gone through the FM modulator. So if you're looking to see the 19 kilohertz pilot and so on, you can't see it at this point. You have to be able to FM demodulate this blob, and then you will see the left plus right at baseband, and you will see the 19 kilohertz pilot and the 38 kilohertz subcarrier. But what do we see on here? We see these rectangles over here. This is HD radio for FM broadcasting. So those are signals that are being carried along with the 88.7 megahertz carrier. They're a form of frequency division multiplexing also, and those sidebands are sitting above and below the centralized carrier. So unless you have a SD receiver, you can't do anything with them, and to support legacy, they're not interfering with the primary FM broadcast. There could also be other subcarrier signals because the FCC allows that in FM broadcasting. And here's just a higher signal. I don't know what that station is, but let's just listen to it. In the midst of you, beyond the music, this is KTLF, beyond the noise, 90.5 megahertz. So I know from listening to it in my car that it has multiple HD channels on it, and that might explain why the upper sideband has got a funnier shape to it. Can't remember what sits in between them. Like rain, washing my This is the station that's at the Air Force Academy. Some of you probably know this, but it doesn't have any digital modulation on it, any HD signals. This is Lab 6 in the labs. I'm hoping that at least it can be demoed in the day that I return. I've talked to Charant about this. He's going to try to get this to allow you to do something with it. Working with the software-defined radio makes it very easy to tune it digitally with a synthesizer, of course, and then listen to other signals. I think, what did I do the other day when we were in lab? We listened to the weather channel, so 162.4. I'm just using my fingers on the keyboard. 475 megahertz.
Southwest winds up to 10 miles an hour.
I can turn the volume up on that, and I'll switch from wideband FM to
68.
narrowband.
Southwest winds around 10 miles an hour. Sunday night, mostly cloudy. Lows in the mid to upper
And
30s.
then when I was doing this demo, I
Southwind
realized
breeze. 0.16 inches of precipitation fell today, which brings the monthly total to 0.30 inches. This is 0.5. Monday, partly sunny.
and I'm sitting at
High
the
69 to
right now, so I
75.
have no
Monday
reception
night,
very good
mostly
here.
cloudy.
Okay, enough of that. I want to go through a little bit more and finish off the chapter, and then if I'm feeling up to it, I'm going to look at Project 2 briefly. So what remains in Chapter 4 is the performance of all the modulation systems we've talked about so far in noise. So all systems are subject to additive noise of some sort, and that's the N of T. So some information that I believe appears at the end in Chapter 4 is just comparing what's called pre- and post-detection signal-to-noise ratio to form a figure of merit on the performance of different modulation schemes. So this is the picture. Pre-detection SNR says that you would put some bandpass filter out in front of the received signal, and you would measure the total received power in the signal divided by the noise power. And this is going to be a common factor for all signals. As received signal-to-noise power, signal-to-noise ratio goes up in what's called pre-detection. That's along the axis, the x-axis here. Now, depending upon the scheme you're using, you have a different type of demodulator, whether it's FM, PM. Digital modulations could be included in this, but I'm going to restrict it to analog since we're comparing it on signal-to-noise ratios of the output. So if we're talking straight double sideband, single sideband, or quadrature multiplexing, QDSB, I guess that's the note in here, all coherently demodulated, we get this blue line. So we're just getting pre-detection SNR goes up linearly with the received pre-detection SNR. There's no particular advantage with one scheme over the other. You have to have a certain amount of bandwidth to get your signal power through, and as you increase the bandwidth, the noise power goes up proportionately because you're letting more noise in. But when you go to nonlinear schemes such as FM, you can expand the bandwidth with the deviation constant. So you can make the bandwidth, according to Carson's rule, get wider as D gets larger. So FM broadcasting can get much higher post-detection SNRs, which are these red curves, when the bandwidth is made wide. You occupy more spectrum, which is a natural resource, but you get good performance. You get a return on your investment. PCM, which you explored in problem 2 of project 1, has this characteristic that as the number of bits in the quantizer 256 corresponds to 8 bits. 8 bits, and 64 corresponds to, my math is not, I'm not thinking correctly here. 256 is 8 bits, 4 bits, 6 bits is 64. So this is a 6-bit system or 8-bit system. And you made some observations on this. It flattens out, and then as the channel noise on all the nonlinear schemes, they all suffer the same phenomena. As you drop the pre-detection SNR down lower and lower, you go through a thresholding phenomena where the signal just gets lost. And that's part of what we were looking at with the interference, in a sense that you have a threshold. But once you're above the threshold, you get very good performance. And all the nonlinear schemes have this phenomena. To me, it's kind of a fundamental rule of modulation in general that this holds, and that this sort of characteristic holds. If you're listening to AM radio, let's say, driving between here, heading towards Kansas, you can listen to the strong signals from Denver just gradually fade away as the signal gets weaker. It gets down into the noise more, so that's this vertical axis, whereas the digital schemes drop out and the FM schemes drop out. When you hit a certain radius, you're below threshold and it's just gone. So sort of a phenomena there with the modulation types. So where are we going to go from here? I'm just going to give a brief introduction to Appendix A. When I come back on the 5th, I want to have at least you have some familiarity with it. The first parts of Appendix A have to do with the source of physical noise. Thermal noise is the main interest here. There's also shot noise, and there's formulas for that in Section 1 of Appendix A. Then the most interesting part that I'll want to zoom in on for the lecture, besides doing the exam review, will be characterization of noise in systems. And this is things such as noise figure, noise temperature, effective noise temperature, cascading systems. As an example, attenuators, noise figure is the attenuation value. We'll look at that. And then how to do a free space propagation example, like for a SATCOM link or just terrestrial link. So these are things we'll be talking about when I return. The physical side of it just has to do with the physics of thermal noise and agitation of electronic devices, not at absolute zero. So we have atmospheric, solar, cosmic, man-made sources, and the most dominant effect that we run into, unless we're near a noise source, which my understanding is if you live near plywood manufacturing plants up in the Northwest, you get from the inductive heating that they use to make plywood, that produces a lot of interference, is my understanding. But some of our LED light bulbs can produce interference that is unwanted. They're low power, but they produce interference. Look that up on Google. You can read about one LED bulb is not the same as another in terms of noise they produce. So thermal noise is Nyquist's theorem, which is this formula right here, involving these physical constants. I will get into this, but I'm just sort of zooming past it. And then the other aspect of this is Nyquist's formula. Nyquist's formula just says that the noise generated across the terminals of a linear network, passive network, is just a function of the real part of the impedance looking into the network. And this is a factor in how an antenna has an RLC type behavior or approximation, has some reactive impedance looking down the line towards the antenna from the feed line, and this factors into noise that you have at your front end of a receiver. We'll explore this more though when we get further down in this chapter, and this will come up when I return. It'll go quickly, but it's not very complicated. So if you want to work Appendix A problems, as soon as you get there, you can take off and do them. There's not very much complexity. Here I used a SPICE-like simulator to model noise. LT-SPICE, you can do noise analysis in it. There's a circuit that has a capacitance and resistors in it, so you can see Nyquist formula in action right there. So, okay, so I'm going to depart from this, and I'm going to go look at the project. And really not too much changed in the project from when I previewed it to you on Tuesday, but I'll just get it up here so I can have it up here. The main focus of the project is a digital communications link, and everything is built for you. What you're doing in this project is just doing experiments with the code and the samples that are in the sample notebook. So you're not doing anything extremely exotic, but you do have to read this document and then understand what's going on in the Jupyter Notebook. So the Jupyter Notebook for Chapter 4 is right here. So once you get this notebook launched up by running the starting cell, I have some preliminary information on statistics and the Q function. It's just in there as information. It's not something that you have to use at all in any of the tasks. But then you will be using the QAM, quadrature amplitude modulation functions. And so now I'll jump back over to what is on the web page. And so data bits come in, they get split into an A and a B. So we're doing this quadrature multiplexing scheme. We're sending a stream, a waveform stream on the in-phase channel or cosine channel, and we're sending another stream on the sine channel. So this is the nature of digital communications for quadrature amplitude modulation, where we're sending signals in both the in-phase and quadrature, and both processing chains here are similar. We produce a waveform by driving impulses into a pulse shaping filter, and then that goes into 2D to A's, and then things get summed together at the analog space, and then the radio channel. The radio channel has the possibility of co and adjacent channels interfering, and then white Gaussian noise will be adding in as a result of carrying it over into the receiver, which has a noise figure and noise associated with its front end. That's part of Appendix A, of course. And then at the receiver, we have a bandpass filter to isolate the signal of interest from other signals out there. We have the quadrature mixing action going on here to get in-phase and quadrature signals like we saw earlier today. 2 low-pass filters, and then we have A to D converters, so we have a complex signal at this point in the discrete time domain. We have a matched filter to shape the signal so that we optimize the signal to noise ratio at the sampling instance where we make symbol decisions. That's kind of the essence, and we'll be using both rectangle and square root raised cosine. This is the same pulse that was talked about in the course. You're going to hear my dogs getting fed right now. There'll be some excitement going on here in a moment because I'm sitting in the kitchen at the house we're living in. So here's the in-phase quadrature signal, and this is the transmitted signal. The transmitted signal, if it's just binary quadrature amplitude modulation, we just send bits as +1 and -1. There's nothing going on in the quadrature channel for BPSK, binary phase shift keying, but when we send it as, say, 16-bit QAM or 64-bit QAM, we have 64 different red dots on here, and 6 bits associated with each of those dots, 3 bits to control the amplitude in the in-phase axes or I-axes, and 3 bits to control the vertical axes.
Sit. Sit.
The dogs behaved beautifully. You may have heard my wife in the background. At any rate, one of the interesting things that goes on with detecting these signals at the receiver is you have to be able to determine which you have to determine where each of these signal points lies at the receiver when it's got noise added to it. So we put a rectangle around it, or a square actually, and it's called the decision region. And for the 64 QAM, there are 64 of these rectangles. Some of them are open-sided, some of them are on the corner, 4 are on the corners, but they're all a little bit different formula. This is part of what second semester of comms goes through in more detail. But an interesting property of the signal here is that it's been gray encoded and then it gets gray decoded. So gray encoding means that we're mapping the 6-bit patterns with a gray code. And if you look at this particular example here, we see 6 bits corresponds to 6 ones corresponds to this location. We're most likely to make errors in either of these adjacent cells or rectangles, but the gray encoding ensures that these most likely places to make errors will only differ by 1 bit. So this is this bullet down below here. It's just telling you that the gray encoding helps preserve the integrity of the signal by minimizing the bit errors through the gray code. White Gaussian noise perturbs this, and the example here just goes through some analysis of how the tail of a Gaussian PDF factors into the calculation for BPSK. For the quadrature scheme that we're looking at, QAM, it's a little bit more complicated than that because you have differences from the different points in the 64 location QAM signal. We send things through a pulse shaping filter. After we encode it, we transmit it with a pulse shaping filter to minimize the bandwidth occupied. And then when we come into the receiver, we filter with a similar matched filter right here, matches with a square root raised cosine. We synchronize in the time, and we have the carrier synchronized. I'm not showing that over here, but carrier synchronization is also present along the way here. I'm not having any modeling with carrier and timing. Well, you are going to model with timing impairments, but we're not implementing phase lock loops anywhere. So our signal natively is at baseband, but we can easily shift it to a higher frequency, and I just show a quick little example of how I could multiply and shift the signal. You got a chance to play with this in Project 1, Problem 1, a complex baseband signal, or a signal at one frequency and moving it to another frequency. This is more details on the receiver. Because we have a QAM decoder with gray decoding, what comes out is a serial bit stream. So when we want to analyze the performance of this system, all I'm having you do is look at serial bit errors. So we get serial bit errors detected with a function in here called BPSK BEP, so bit error probability. So the fact that I can use a function designed for BPSK doesn't mean the modulation is BPSK. It just means that the bits are serial bits, so we can use that function to check to see if bit errors are present way out over here, because we have a copy of what the underlying bits were put in over at the transmit side. And that's what this function is doing. It takes the TX data, takes in the RX data, it tries to line the two streams up with a correlator set to 1024 points, and then once it does that, it's able to get the bit errors. And if the bit errors were everywhere, it would not function, but it's aligning the two streams of data, kind of like the sync pattern does. And that's just demonstrated here. I did a very simple example where I set the signal-to-noise ratio equivalent on the symbols to 22.78 dB with 64 QAM, and I run through the BPSK BEP on the serial stream, and out of 600,000 total bits sent, 498 were in error. That works out to a ratio of 498 over 600,000. That says the probability of a bit error in the serial stream is 8.3 times 10 to the minus fourth. That's what the constellation looks like on the scatter plot at the sampling instance in the receiver. And this is the calculation, like I was saying, that's being done in the code. You don't have to write that, you just have to drive the functions. This is a theoretical expression that tells you what the probability of error should be. A bunch of assumptions rolled up inside of this, part of COM2. But here in this example, when I ran it, the theoretical value is 7.72. In the simulation I ran over here, it was 8.3. It was not totally dead on, but it's pretty close in terms of a simulation running with variability due to errors. So let's just jump into our simulation and take a quick look at that point. So I'll drive it down here, just step through. I gave you the PDF of this so you can see that everything renders properly when you bring this notebook in, because if it doesn't, you've got some problems with your code base. So here's the pictures we were already looking at. Here's the example where I'm going to send and decode QAM. This is the 64 QAM. I'm going to decode it with a particular signal-to-noise ratio, set it at 15 dB, and here I'll receive it. Created 494 errors, 8.233 times 10 to the minus fourth. This is the theory value, 7.72 e to the minus fourth, so pretty close. Now we go into a waveform simulation, and this is what you're going to be doing at the end, where you're going to be sending alternative data rather than random bits. You're going to be gray encoding this is basic. I'm getting ahead of myself. This is just another bit simulation just to look at waveforms. This is what the in-phase and quadrature parts look like. These are taking on the 8 values in the in-phase and 8 values in the Q. And when we matched filter this right here, we get the matched filtered values sampled every symbol, and we should see on the in-phase and the quadrature, we should see a total of 8 different horizontal lines, and they're not dots connected together because this just so happens, this happens with random data, but it should follow a nice horizontal line saying that without noise present, it looks consistent. If we use what's called an I-pattern plot, we can look at the in-phase and we can see at the sampling instance, we see these nice points, the 8 points in between. It's a waveform, so it's transitioning, And so this is called an eye pattern plot, but we're looking at 8 eyes stacked on top of each other because we have 64 QAM present. If I was to change this sim to run with binary, so if I was to change this value m here equal to 2, then I would see something much different. You're not going to really be doing this, but now we just see it looks like BPSK in phase only. There's nothing in the quadrature, just very tiny values. Match filter that. Look at the data. So we just see 2 different amplitude values all the way along, and then we look at our eye pattern plot, and it's just looks like a single eye, and it's perfect. If I was to add noise into this, though, then it would look different. So here I'm doing 64 QAM with pulse shaping, the SRC pulse shape, and it gives a much more band-limited spectrum, which is what we have up here. It gives a nice band-limited spectrum like this, whereas if I was to rerun this with the rectangular pulse shape, which I could change in my transmitter, I could change it from SRC to rectangle if I was to put in rect instead. You see why we don't want to use that, because the signal and the signal shifted are interfering with each other. So we use the SRC, square root raised cosine, to be able to stack more signals up using an FDM kind of a usage, or frequency division multiple access is the term there. Signals can be next to each other and not interfere. So moving on down the line here, what you're going to be doing is the BEP testing, and you're going to be looking at it with different impairments. So if I go back over here and look at our project, and we're also assuming perfectly coherent receiver. So I encourage you to read all of this so you understand kind of the game plan behind all of this. Pretty much shown you the simulation side of all of this. And then I do an audio example at the very end where I'm sending through PCM, and I'm using the sync pattern because we have a delay associated with this whole process and we need to automate that. So we use the sync pattern, and the correlator that we talked about in Project 1 is implemented here. But you will be doing some basic exercises here with scatter plots and error probability curves. You need to read about that. Make sure you look at these appendices, scatter plots, eye plots, and waterfall curves, which is the error probability plot, is the very last topic in here. When you put impairments on, which is what you'll do in task 2, you'll have either a phase, you'll have phase jitter, which will push this curve out and flare it out, or you'll have timing error, which will also push things out. And pushing things to the right of the theory curve down here means that we're getting some impairment due to some imperfections in the received signal and in the implementation of the receiver itself. But I'm about out of gas now. I don't want to keep going any longer. What I want to do is just jump back up here to have you do something very important in testing. And that is, I did make some changes. I talked about that on Tuesday to Scicit DSP-Com, both for PCM and for coding. So you need it for PCM, and it's possible that without doing the upgrade, you will have a problem when you do 16 bits per sample in the PCM. So I'm going to let you figure that out. But here, what I've done in the notebook is just 8 bits. So here I do an audio test. Here's the rework of the functions from project 1. I just cleaned them up and added some more features that were important. But here we're going to run an example where we're going to bring in some samples of speech. We're going to bring in 10,000 sample or 60,000 samples of speech, encode it with 8, and there's an option to take that in. After we encode it, we're going to add the sync pattern to it, and then we're going to send that in using this option, external data, rather than random data, which is what you'd get if you didn't use none in there. We can find out. Normally it's the number of symbols, but you have an option to put in none and then put in external data. So that's talked about down in here. And I'm demoing that. So here we're going to transmit it. I didn't run all these functions, so I have to run these guys. I didn't create my sync pattern. Got to run that one too. There it is. This was just copied over from project 1. So now everything's been run, and we're running at a high signal to noise ratio. I have the random time shift that was originally used in project 1 turned off. You can see that in here. It's set equal to false, and that's the way I want you to use it. And then I come along down here and I implement the receiver on this. I do that right in line here, but I have it a different setup, I think, for example, for sampling. So I come down here and I'm reading my code again because I'm starting to. I encode, add noise, match filter, manually synchronize. This takes the place of a phase lock loop. Gray decode, do bit errors. Okay, so I have that done. There's no noise in these, so they're not doing much of anything. They're just like straight lines again. Now I'm going to come down here in the receiver and I'm going to find the sync index from the sync pattern, and then I'm going to plug that into returning the packet stream or framed stream into just raw PCM bits without the sync pattern included. And then I can pass that into the PCM decode, and I get back my data. And if I go ahead and save that data.
The little tales they tell are false. The door was barred, locked, and bolted as well.
So that works well.
The little tales they tell are false.
That works well, but you are going to be running this not with 8, you're going to be running it with 16, and you're going to be using 256 QAM, so very dense constellation set. So you'll be doing something a little bit more exotic. I think that's all I want to say right now. You're going to send me a picture like this, and if it doesn't look like this, something's not working. So you don't need to send me the WAV file, because I'll believe it if I see this pattern right here. It's all coded already. If you have problems, though, you want to send a WAV file, I'll listen to it and see if I can understand what's going on. But at any rate, carry on, and I'm going to carry on with dinner. So this has been a long stretch for me, and I'm going to shut down at this moment. Bye for now.